Ναι, τέλεια. Ευχαριστώ πολύ. Okay, so good morning, everybody. It's my pleasure to be here and present this topic on statistical time series methods for vibration-based robust structural health monitoring under uncertainty. I'm Spillos Fassois, as indicated before, from the University of Patras in Greece. So I will present just a brief overview of some of the principles. I do not really intend to go into details, but to stay on the general approaches. Let's see if this works now. It does not seem to work, but I can do it from here. It's okay. It's okay. Okay, so nothing works? Okay, here it is. Yes, that's fine. It's okay. No problem. That's okay. It's okay. It's okay. The pointer is the important thing. I got the pointer, so I'm okay. It's okay. Don't worry. Just the pointer is the important thing. Thank you. That's fine. That's all. Okay, so here's an outline of the presentation. I will talk about structural health monitoring and random vibration based. Then I will talk about robustness. I'll talk a little bit about robust methods. I want to present some application case studies very briefly and of course draw some conclusions. So let's move on. Here's a brief introduction into what structural health monitoring is all about. And I present it here in terms of an example from an aircraft. This is specifically a UAV. But of course, these methodologies apply to any kind of structures and also civil infrastructures, to vehicles, and so forth. But we just happen to work quite a bit with the aircraft industry. So that's why I'm using this example here. But also you will see some other examples from the wind energy and so forth sector and so forth. So what is the idea here? The idea is very simple. Basically, we're talking about a mechatronic application. It's a mechatronic system. And what you have is sensors. So you put sensors on a structure. These sensors can be, for instance, accelerometers. They can be used, they can be PZTs, strain gauges, maybe different types of sensors depending on the case. But one has sensors, and so these sensors are operating continuously all the time. And then there are processors at specific places that will collect the signals measured. They do that in real time. They will process the signals. And there's a central unit that is making the decisions as to whether everything is all right with the aircraft or the structure in general, or whether some action is needed. There are some advantages of using vibration signals for doing this. One of the advantages is that vibration, for example, is a global phenomenon. It involves the global properties of the structure, so you don't have to measure locally and you don't have to have many sensors. I mean, the number of sensors that I show here is quite large, I would say. We would prefer to do it with fewer sensors, and this is what we're trying to do. Also, another advantage of vibration is that it is naturally available. So one does not need to excite on purpose, but one may just use naturally available vibration. For example, when the aircraft flies, we have the vibration because of turbulence, because of the engines, and so forth. Okay, so let's move on. No. Okay. So we have different levels of structural health monitoring. The first level is to do damage detection. Then we want to do characterization and size estimation. And also we would like to do damage localization and, if possible, some prognosis, remaining useful life estimation and so forth. And we're talking about different types of damages. For example, here is a damage on a composite structure. This is from an aircraft structure from one of our projects with the Israeli aeronautical industry. This one comes from. And it's a damage that is caused by impact, and it is essentially non-visible. What we see here now is thermal tomography. But if we look with a naked eye, we will not be able to see much. I can take it here, so I don't bother you. Okay, it's okay. Okay, So what is the idea for random vibration-based structural health monitoring? A damage will cause some changes in the dynamics, and these changes in the dynamics will appear in the vibration characteristics. So essentially what we do is we try to reverse this relationship, and from the vibration characteristics to go back and detect, diagnose the damage. This is the idea. Now, for doing this, we have either physics-based methods or we have data-based methods. Physics-based methods require a physical model of the structure, and this is, it can be done by using, for instance, finite elements and so forth, but it's quite complicated, and it needs to be updated and so forth. So it's a complicated process, plus it will require a considerable number of sensors. Whereas if we go into data-based methods, which is essentially machine learning type methods, we're talking about machine learning, we can have very partial models of the dynamics. So small models that do not cover the whole spectrum of the dynamics, but cover the essential dynamics. And we can also use a small number of sensors. Now, the data-based methods, the methods that are using essentially machine learning, can be based on models like this. These are stochastic models because in general here we have stochasticity because of turbulence, because of a number of factors. You have a lot of stochasticity, of course. And so we're using stochastic tools like statistical time series analysis and so forth. And you can have different types of models. Some can be non-parametric like autocovariance functions or power spectral density functions. Some can be parametric like transfer function models or state space models and so forth. Okay. Now, in the classical approach, one is using a baseline phase in which one collects a signal or a number of signals from the structure in healthy state, and then using the properties of the estimator. So, for instance, here, if we're using the power spectral density estimator, we know by the properties of this estimator that this follows a specific distribution. For instance, it is a chi-square distribution here. And then when the aircraft flies again and we want to monitor its condition, we repeat the procedure, we have a fresh estimate, and then we formulate a hypothesis testing problem to see whether the current spectrum of the structure is identical to the spectrum that we had in the nominal, in the pristine condition, in other words. And if this is true, then we know that the structure is healthy, otherwise we know that the structure will be damaged. So this can be formulated by using an F-test. So we use the F distribution, as you can see here, and we pick up a risk, and then we have an interval within which this quantity here should lie, in order to have the healthy state of the structure. Otherwise, we declare that we have some kind of problem with the structure. So this is the classical approach, but there are some problems with the classical approach. And the problems that are coming up with the classical approach is that we do not fully account for certain conditions, like varying conditions, like environmental conditions or operating conditions or material and manufacturing conditions or uncertainties. For example, if we're talking about environmental conditions, the structure, for instance, is affected by temperature, by humidity. If we're talking about operating conditions, the structural characteristics will be affected by the payload, by the boundary conditions, by the mode that the aircraft operates under. For instance, if it is flying a specific way, if it's landing, if it's taking off, and so forth. So all this uncertainty is creating essentially false alarms. If we try to apply a classical approach, you will get a lot of false alarms, and we have to somehow account for this. Now, why is this happening? The reason that we're getting false alarms in this case is that if you look at, let's say, the spectral characteristics, which is the spectrum here versus frequency, okay? So we're looking essentially at the dynamical characteristics in the frequency domain. Under the healthy state, you have a zone, because of uncertainty, where your characteristics should lie, okay? And it is not a curve, it's because of uncertainty, you have a zone. And then whenever you have a damage, it is quite possible that the characteristics under damage will fall within the zone that you have in the healthy case. So you cannot easily distinguish between the cause of the difference in the dynamics. Is it coming from damage or is it coming from those varied conditions that I mentioned before? This has been a major technological barrier in adopting these technologies, and this is the reason that if you look at the aircraft industry and also other industries, they're trying to use the technology, but they do not consider it as being mature enough to trust it yet. So we need developments in order to be able to effectively address these kinds of issues and develop a mature technology that can be trusted and can be installed on actual aircraft and other structures. Okay, here I have an example from a project where we have a population of structures. These are also coming from a UAV. So this is a boom. You can see it here under experimental testing. So we have an exciter here and we measure at different points by using accelerometers, or other sensors can be also used. It's a composite structure, as you can see here. It's right here on the UAV. It's this kind of structure. Okay. And we have another. We have 31 of these structures. And the interesting thing with these structures is that the variability coming from manufacturing is very important, as we will see. But before I go into that variability, let me tell you a few things about the damages. So here we see that by infrared thermography, we see a damage here, which is caused by impact. Okay, on an aircraft, you often have impact. For example, a bird can collide with aircraft, so that can cause some problems on the structure. So here we have an impact with a low energy, 13 joule. This is a little bit higher energy, 18 joule, and this goes to 24 joule. And this impact is invisible, totally invisible by naked eye, and it's barely visible by naked eye here, and it becomes visible when it is the larger one. Okay, and these are the thermography images that we're getting. So we can see it on thermography, but thermography is not an automated procedure. I mean, you have to bring the aircraft down and you have to scan it and so forth. Here, what we're trying to do with SHM is to develop an automated procedure that can give us diagnosis automatically and in flight. Okay, thermography cannot do that. Okay. Let's see. Why it does not want to move now? Okay, here it is. So I talked before about the uncertainty. So if you look at this population of structures, you can see here 23 of them, and you have some variability in the mass. We have variability in the wall thickness, cross-section dimensionality variability, and so forth. These are coming from the manufacturer. But of course, on top of these, you have other effects, like temperature effect and so forth that I mentioned before. So anyway, if you look, because of all these uncertainty, if you look at the healthy dynamics in the spectral domain, so this is the frequency axis, and this is the spectrum here, you see that we have a zone, the green zone, that represents the effects of uncertainty on the healthy dynamics. And then once you have a damage, which are the red curves here, then these red curves pretty much follow or pretty much fall within the green areas. So it means that it is very difficult to diagnose damage because of uncertainty. It is becoming very, very difficult. This is for low energy impact, but it is also not very different when one goes to a higher energy impact. So we are having problems because of the uncertainties. Oh, let's see. Why is that happening? Just one moment, please. Okay. So if we try to apply the classical techniques, then this is what we get. I want to stay here. This is based on many experiments. Each dot that you see here corresponds to one experiment. So we're talking here, I don't remember the exact number, but we're talking about maybe 1,000 or perhaps even more experiments in order to have some reliable results. The blue marks are with the healthy structures, and the other colors are by damaged structures. So you see that for damaged structures, there is a distinction between the color points, the other colors, and the blue ones. But also we have a lot of overlap, and this overlap is creating the problems, like it is creating the false alarms and so forth that I explained. And if you look at the receiver operating characteristic curve, which is here the true detection, the probability of true damage detection, and the probability here of false alarm, then we would like ideally to have a 0 false alarm probability with 1 probability of true damage detection. So ideally we would like to have a curve that looks like a step, but we're not there. If you apply different techniques, as I show here, on this kind of problem, what you get is a performance that is not good at all because of the uncertainty. So the question is how to handle this. And here is an overview of how we can handle this. Essentially, we have to model the healthy dynamics, the healthy structural dynamics under uncertainty. This is the real question, what we have to do. And there are two types of approaches, implicit approaches, or implicit methods if you wish, and explicit methods. In very simple terms, I don't want to go into the details. In very simple terms, implicit methods, what they try to do is they try to develop a model that does not depend on the uncertainty to the extent that this is possible. Explicit methods will develop a model that fully captures the uncertainty effects. So it's two different philosophies. In one, you do subtraction. In the other approach, you have all-inclusive approach. Two different approaches. And there are different methods in each type of approach. Both of them can work pretty well. And here are some of them. Okay, let's not stay here for a moment. For example, I just present some examples now, very, very briefly, of course. One method that is based on machine learning is using the PCA. PCA stands for Principal Component Analysis, which is a very well-known statistical technique, basically. And once we have data, so this is the feature space. Here you select a feature, and you have a feature space. I saw this here as two-dimensional. In reality, this can be very high-dimensional, like a space of 1,000 elements, and so forth, the dimensionality of 1,000. And so essentially, you look at the directions in which you have the maximum variability. For example, here you have a lot of variability here on this axis, and you have also considerable variability along this axis. So the idea in this case is to eliminate these two axes and look at other axes in your data which are less affected by uncertainty. This is the idea. And hopefully then you can detect the damage on those axes much easier and more reliably. Of course, this technique is based on PCA, as I said, but one can also utilize neural networks and other types of processes in order to analyze the data in different spaces. And if we look at some results that are obtained by, for example, the PCA, as I mentioned, you can see that we can improve the performance. We're coming closer to this point. You remember, this is the magic point here, the point where we want to be. And we're coming closer to that point compared to what we had before. So indeed, these kinds of methods can help us do a lot better. Of course, they're not perfect. Another approach has to do with classification type methods. We can use different classification approaches. And here, let's see what happened with this. Okay. Oh, I think this is a PowerPoint that is doing something, but it's okay. If necessary, I have a PDF version, but I think we'll be all right. If you use classification type approaches, like the K nearest network neighbor approach and so forth, one can improve performance. So we can achieve performance, as you can see here, quite a bit. Now we're getting closer to that critical, to that magic point. This is for low impact damage, so this is the difficult case. And if you go to high impact damage, which in reality is not very high, but nevertheless we call it high, and then the performance comes very, very close to being ideal. So these kinds of classification type approaches can help us get very good results in structural health monitoring. Another possibility that is an all-inclusive method basically is to to go to the feature space that we have here and to model the variability by using probability density functions. Of course, one would like to use an easy approach like a Gaussian approach, but a Gaussian approach is not going to work in almost all cases. We have different kinds of distributions, so one could try to find appropriate distributions and so forth. One possibility that is relatively simple is to use a Gaussian mixture model. And by using a Gaussian mixture model, we can approximate this distribution quite well, actually, in many cases. Here is an example of the model that we're using. This is a statistical time series model for the vibration response, past values of it. These are the coefficients of the model. This is white noise that is generating the vibration. And these AIs are random variables. Actually, all the AIs together, they formulate a random vector that follows a non-Gaussian probability density function. And we have to estimate this by using appropriate approaches and then have a model of the dynamics under uncertainty. So this is the idea. There are some details here that I will not go into. And here you can see this model. You can see here one Gaussian model that is basically dominating here. There are some smaller ones that are not very visible, and there's another one visible over here. So we have a Gaussian mixture, and in other words, an overlap of Gaussian distributions, right? And by using such approaches, we can also get very close to the ideal, as you can see here. So these approaches are behaving, I would say, quite similarly. Although they are not the same, they're quite different from each other, but the approximations that we get are quite similar. And this is encouraging because it tells us that no matter what you use, you can have a good result. Of course, one can do some fine-tuning to try to find for specific problems or specific categories of problems to try to find the best approach, which is also possible to be done. Okay, there's another approach that we've been developing over the past several years, and we are approximating deterministically the feature space. Here, basically, what we do is we try to approximate this space by using ellipsoids. So it's another approach. This is not probabilistic. We're just using ellipsoid approximation. This is also of interest and can also give good results. So if you see here for the high impact, the performance is very close to the ideal. For low impact, not so much, but it's along the lines of what we got before, very similar. Okay. Another method that we have also been developing in the past few years is a functional model-based method. This is also an all-inclusive method, and it can also give good results. I will not go into the details, so these are the technical details here on how this is done. I will just say that we have a model of the dynamics. This is the model of the dynamics, which is a time series model basically. And then you have parameters that are functions of the uncertainty vector. And through this, you can essentially accommodate the effects of uncertainty. And here, if you apply this technique, then we're getting results that are very, very close to the ideal, essentially coinciding with the ideal in this case, and also in this case, which is small damage and larger damage. So this is also a very promising approach for solving the problem. We have also worked a lot on damage localization, and again, I will not go into the mathematical details, but I will just say a few words about the experiment that has been done in the laboratory here. This is a lab experiment, and we have this aircraft structure. Oops, I'm sorry for the Chinese. This is PowerPoint problem, but does not matter. That's why I like to bring my PDFs with me. Now, for some reason, I decided to open the PowerPoint, but it tells me that I should not in the future. It's better to work with PDFs. Anyway, that's not matter. Forget the right part. The left is a... I'm sorry, what? Yeah, okay, yes. Right. So here we have a structure. This is, it's a scale structure, but you can see the dimensions. So this is like 2 meters, 15 centimeters. This is 176 meters. So you can have an idea of the dimensions. Of course, this is scale. It's in the laboratory. And we excite at a point here. You don't see the exciter, but this is the point where we excite. And we measure the vibration here, and we measure the vibration there. Then we can simulate damage at all these points. And the way that we simulate damage is we put a very small coin. So we locally increase the mass. So this changes the dynamical characteristics. And then the problem is using the signal, either this signal or that signal, the vibration signal, to estimate the exact point of the damage. And this is quite impressive actually, because we can estimate the point very accurately. For instance, we have a damage at this point, and we estimate it very, very close to it. You can see a blow up here. Look at the scale. This is like 6 centimeters. We're talking about 175 meters, right? So this is a blow up. This is the true point of the simulated damage. And in one case, with one sensor, we estimate this point, and this is the uncertainty zone. So it is touching the actual point. And with the other sensor, we estimate this point, and this is the uncertainty zone. So the error is really very small. And we have another example here, another example there, another example there. So this is quite impressive. And we have more Chinese on the bottom. Okay. I'm coming now to some case studies. I don't want to make the presentation too long, just a short one to give you the idea. So this is a prototype system that we developed with our collaborators. It's being published in some papers, you have one here. This is a prototype unit that we built, and this is intended, it's a prototype unit, but the ultimate purpose is to have a smaller unit on UAVs and small aircraft and so forth. And of course, bigger aircraft in the future to be able to do structural health monitoring. So this is the unit that we developed with our collaborators. And this is the GUI, the graphical user interface. So it is collecting signals and it is analyzing the signals here in the frequency domain. We have an undamaged boom over here. And here it tells you in green that everything is fine. The structure is healthy, no problem. You can go on. And in this case, there is a damage and it becomes orange. And it tells you that you have a problem. And you have to go to maintenance, or maybe if the problem is significant, you have to bring it down right now. There's a threshold here and threshold over there, and how significant the problem is has to do with how much this threshold is exceeded, basically. So this is a demonstration that we have done at one of our collaborators, one company. And you can see, I showed this before, it's this boom right here, as I said, and this is from the experimental setup. And these are the results of many, many experiments. As you can see, each dot represents an experiment. These are healthy experiments. You can see we're below this threshold, and once you have damage, you're above. And so this worked actually very nicely, no problems at all. I would say, better than our initial expectations. This is another example from the energy, wind turbine energy sector. And we have a wind turbine here. This is in Denmark at the National Technical University of Denmark. And this is in collaboration with B&K. And in one of the blades, there was a small damage created. You can see it here of 3 different dimensions. This was progressive damage, 15 centimeter, 30 centimeter, and 45 centimeter. This is a diagram of the blade, so the damage is here. And this was instrumented by accelerometers. And each time we used just one accelerometer to see whether we can automatically detect the damage by using the acceleration signals. I want to emphasize that the damage is really small. I mean, we're talking about a blade that is 13 meters long. So the dimension of the blade is 13 meters, and we're talking a damage that is 15 centimeters or 30 or 45 centimeters. So the damage is really minor. You can see it here, right? It's really minor. So it is a very challenging problem to see whether we can detect this kind of damage. And we apply the techniques that I mentioned before, and this is what we're getting. We're getting very good results, at least these are different methods in different colors, right? But you see one of the methods in green over here comes very, very close to the ideal performance. So we can detect it very well, and we're talking about the small damage here, only 15 centimeter. If you go to 30 centimeter, this becomes ideal by the green method, and if you go to 45 centimeter, of course, the same. So it is quite impressive that this could be achieved by some of the methods. But of course, also you see here the different performance of different methods. Different performance by different methods, okay? So the performance is not exactly identical. You have some variability, but we have enough experience now, depending on the problem and studying the problem a little bit, to be able to suggest the best method. Or another possibility is to use 2 methods or maybe 3 methods and do some kind of fusion on the decision-making procedure. We're also working on this. This is an example from railway vehicles. This is a project with the Athens Metro. And you see here a schematic diagram. You see where we used accelerometers, so the positions for the accelerometers. And then we looked at some damages. Okay, you can see the accelerometers actually here in these photos. Okay, and we had some damages on the vehicles. One of them was a problem in the lateral damping of the vehicle. The lateral damper had some kind of leakage. Okay, so we knew it was not good, and we tried with a healthy damper, and then we put the damper with leakage. We wanted to see whether we can automatically identify the problematic damper. Okay, and the other, this is with red, the curve with red, and the other is the air spring. We deflated the air spring a little bit. Okay. Now, as you can see, these are experimental results. So each point here, again, corresponds to an experiment. So we've done almost 1,800 of experiments, of many, many experiments. And the vehicle is moving, right? Traveling all the time. We did this, after hours, of course, early morning hours. So we did not want to intervene and interfere with the passengers or anything else, okay? Anyway, so the performance here for the air spring is perfect. We could very easily detect the air spring problem. Now with the lateral damper, it's less evident. You see the performance is okay, but it's not ideal. We would like to have even better performance, but this is where we stand with this problem. It's a problem that we're still looking at, and we hope to improve this result in the future. We have some ideas, of course, on how to do this, but we're still working on it. So in order to conclude this presentation, I do not want to go into details, as I said, for today. I talked about random vibration-based structural health monitoring. We primarily use machine learning type approaches, and these approaches have come of maturity to some extent. We still have problems, these are here, but some of the advantages is that we can have high diagnostic performance. I would like to emphasize that these are low cost. We're talking about a very small cost for the unit. For example, you can have a unit with a few sensors at a cost, at mass production, I believe it will be around 1,000, maybe less. If we don't talk about mass production, the cost can be like 2,000, 2,500, but it's really low cost. For an aircraft, for example, or a vehicle that costs, quite a lot more, of course. So we're talking about low-cost solutions. We're talking about operation with a limited number of sensors. This is important. We don't want to place sensors everywhere. It would make our life easier, but this is not our objective, because you have to increase the price, pay more, and then you have an issue of reliability, because sensors also fail. So the more you have, the more reliability becomes an issue. So it is important to have a small number of sensors. It is important to have natural excitation like we have in aircraft or in railway vehicles or on bridges. It's also important that we don't go to high frequency signals, because we don't have this high frequency content under natural operation. And of course, we have something that is highly automated. Of course, this is the objective. Now, what are the drawbacks? These are the advantages that we have in this technology. Now, the drawbacks is the training. The training can be extensive in some cases for most methods. Now, we're trying to develop methods that require a lot less training, and we have some very good results on this as well. So this is important, to reduce the training. Lack of label data. In other words, it's very difficult sometimes to have actual faults or damages happening on a train, or on an aircraft. So we only have the healthy case. And so we have to stay unsupervised, as it is called in machine learning. We're talking about unsupervised methods. So this is a limitation, that we don't have this kind of data under damage. Very, very often we do not. And another issue that we are looking at is some of the methods' hyperparameters. Of course, in every method there are hyperparameters. And these hyperparameters, they have to be selected very carefully, based on experience, based on some optimization, and so forth. This can be also subjective, or it may be also be time-consuming to do. So this also somehow has to be improved. So these are the weak points, I would say, the areas where we need to improve. We achieved a lot so far, and I'm not talking about our laboratory, I'm talking globally. The global community has achieved a lot, but there are also some important issues that are still here, and they need to be taken care of. I would like to give credit to my colleagues who have participated in these projects that I mentioned. I mentioned some of them. Of course, we are running many more projects. And also, primarily, I would say, to my PhD and master students who do all the hard work, and we just supervise, how it is. Okay. And with this, thank you very much. If you have any question, I would be happy to try to answer. Of course, you can visit our webpage, and you can see more, download papers, whatever. And here is a typical vibration signal. I think this is from an aircraft, if I remember well. It's a real signal, like the ones that were processing in this technology. Thank you very much.